Our next example is the oscillating pendulum. So what I have is a pendulum which has been displaced to the left, and the angle of displacement is theta. This pendulum is going to be released and it's going to swing back and forth. And I want to know what the equation is for this angle as a function of time. And so the way I formulated this problem is I'm asking for that angle as a function of time, provided that I know the initial angle is some amplitude theta 0, and the pendulum itself is released from rest, so that it's initially at rest at the moment that we start our equations. Just like in the train car problem, we're going to have a force of gravity which points down, and a force of tension which points up and to the right, and makes an angle of theta with the vertical. I can form my system of equations, which are identical to what we had before. But now I could potentially have an acceleration in both directions. And these equations are going to need to be massaged a little bit in order to get a reasonable answer. Okay, so what I'm going to do is I'm going to introduce some approximations. And in particular, I'm going to introduce what are called the small angle approximations, so that I can get an answer that's valid for angles which are sufficiently small compared to the number 1. Okay, so we're taking about angles that might be, say, like less than 10 degrees or something like that. 10 degrees expressed in radians is much smaller than the number 1. So these small angle approximations allow me to approximate sine of theta as theta and cosine of theta as 1. And these are based on a concept called linear approximations. A linear approximation is when you approximate a function in the neighborhood of some particular point by its tangent line. Okay? So for instance, if you have some function y equals f of x and x, and you have a point x naught, in the neighborhood of that point you want to approximate the function. And what you do is you construct the tangent line to that function, which would be y equals L of x in my notation. And the tangent line will be a good representation of the function as long as you don't get too far away from x0. If you do get too far away, you'll start to see a big gap. But in the neighborhood of x0, it'll be a good approximation. Okay? So linear approximation is basically a function which follows the point slope form for the equation of a line, and it uses the derivative at a particular point to estimate the slope of the tangent line, and it uses the value of the function at a particular point to establish where the tangent line is, and you can use that to simplify expressions as long as you're not going to stray too far away from the reference point. So small angle approximations for sine and cosine are based on a reference where theta is equal to 0. And so if I apply that, then L of theta for sine would be sine of 0 plus sine's derivative, which is cosine of 0, times theta minus 0, which works out to just theta. And for cosine, L of theta would be negative sine of 0 plus its cosine's derivative. Oh, sorry, not negative sine of 0. It will be cosine of 0 plus the derivative of cosine, which is negative sine of 0, times theta minus 0, which is equal to 1. Okay. So these small angle approximations are going to allow me to approximate sine and cosine in terms of some very simple expressions, and they will be valid so long as theta is not too large. I'm going to need to get the accelerations in terms of theta and I'm going to use my small angle approximation to simplify them. Simplify the expression for the acceleration. So the key thing to remember is that the acceleration is the second derivative of x with respect to t. And my x for the pendulum is negative L sine theta. And so what you can imagine is, okay, here's the ceiling. Here's my origin with x and y. And there's my pendulum. Here's theta, and you can see the x-coordinate is negative L sine theta. And you can see the y-coordinate is minus L cosine theta. My x-coordinate is negative L sine of theta, and I'm going to take the derivative of that to get the velocity in the x direction. And what I get is negative L cosine of theta times d theta dt, because theta is a function of time. I have to use the chain rule and multiply by its derivative. Then I take the derivative of this, and that's a product rule. First, you get the derivative of negative L cosine, which is positive L times sine, times another d theta dt, which gives me a d theta dt squared. And the next step of the product rule gives me the derivative of d theta dt times negative L cosine theta. And now if I apply my small angle approximations, keep in mind that I'm considering, so if I apply my approximations, this will be theta, and this will be 1. But I'm assuming theta is small, and correspondingly, I'm assuming that the rate at which theta changes is also small, because it's not going to be able to pick up too much speed if the deflection is very small. So this is a small quantity times a small quantity squared, which makes this very small, okay? And when you're doing approximations with quantities that are assumed to be very small, you tend to neglect anything that is like a small thing times a small thing. So what I mean by that is that this is presumed small, and this is presumed to be a small thing squared, whereas nothing in this expression is considered small. Okay, so this is negligible, and I'm left with negative L times 1 for the approximation times d theta dt squared. So the x component of the acceleration is going to be approximated as this expression. Next, we compute the y component of the acceleration, which is the second derivative of y with respect to t squared. And y is negative L times cosine of theta, which I've already explained. And I take the first derivative, and I'm going to get the derivative of cosine, which will be positive L sine theta. But because theta depends on time, I get a d theta dt from the chain rule. Then the second derivative is going to involve the derivative of this expression times another d theta dt due to the chain rule, plus this expression times the derivative of that expression, which turns out to be a d2 theta dt squared. Okay. And this quantity is a small quantity squared, so that is negligible. And this quantity is a small quantity squared, because we're assuming the acceleration is also small, so this is negligible. And so I have, to the first approximation, ay is approximately 0. Okay. So to the first approximation, ay is approximately 0. What this means is, at the level of analysis that we're doing, the acceleration in the y direction is not going to factor in. A more exact solution would involve the acceleration in the y direction, but we don't need it for the level of precision that we're looking at here. And the way you can think about this is if the angle is very small, then the string is more or less vertical the entire time, which means the primary thing that a vertical acceleration would indicate would be a stretching or elongation of the string. So you can imagine, like, here's the string, it's practically vertical, and an acceleration in this direction would really imply that the string is like stretching as the bob accelerates downward. And we know the string's not going to stretch, and the only circumstance in which this number will really be significant is if the string makes a significant angle with the horizontal, with the vertical, so that now we can kind of see a big acceleration that's going to require a vertical component. Basically, you can think of this as basically, as long as the angle's not too big, the primary purpose of AY would be to stretch the string, but the string can't extend because it's taut, it's well made, and so it's not going to extend. And so we approximate AY as being approximately 0. Okay, so now if we return to our equations, we had max equals ft times sine theta. Well, I can replace sine theta with theta according to the approximation. And we had may equals ft cosine theta minus fg. I can approximate ay as being 0 at this level of analysis. Then this bottom equation tells me that ft should equal mg approximately, and I can substitute that into here to get this, which is that max equals mg theta. Then on the next page, starting with max equals mg theta, I can substitute the expression I found for ax, and I find an equation, differential equation for theta in terms of g and l. Now, if you look at this, what you're really seeing is the second derivative of something is equal to some negative constant, this guy, times the something itself, right? The second derivative of a function is some negative constant times that function. Well, this is a harmonic oscillator. And so what we have here is a harmonic oscillator with a stiffness or spring constant, so to speak, of g over L. And that means it has an angular frequency of square root g over L, and the solution is given by sines and cosines of t. It's a sinusoidal oscillation in time. Okay. And so if we go to the next page, this is the general solution for a harmonic oscillator, and with a frequency square root g over L. And it has two coefficients, an a and a b, that multiply the sine and the cosine. And what the a and the b do is they kind of determine where your sinusoid is located along the t-axis. So it's like, is it starting like a sine where it starts at 0 and then goes up and down, or is it starting like a cosine where it starts at 1 and then it goes down and up and down and up? And these coefficients are related to our initial conditions by substituting 0 in for theta, and 0 for time in the expression for theta, which gives me a, and 0 for time in the expression for d theta dt, which I'm not going to work out, but you can try it on your own, and you'll find that it gives you square root of g over L times b. So my a and b are determined by the angle at time 0 and the angular velocity at time 0. I'll come back to that point in a second. So the angular velocity at time 0 is 0 because I stipulated that the object started at rest, and the initial angle is theta naught. And so if you use those equations, you'll find that a equals theta naught and b equals 0. And so theta t for us would be theta naught times cosine of square root of g over L t. So if we're going to make a graph of theta of t versus t, we'll start at theta naught, and it would go down like this. And this would be negative theta naught down here. Something that is interesting to take note of, which I wrote as a note on the previous slide, is that this angular frequency here is completely independent of the mass of the pendulum bob. Okay, so whatever it is that's swinging back and forth on that pendulum, it actually won't determine the motion. All it'll do is it'll just swing with the same motion regardless of its mass. And that's a manifestation of the Galileo's principle that the motion of an object in a gravitational field is the same regardless of its mass. Right? So Galileo had this famous thought experiment that if you drop a bowling ball and a feather in a vacuum, that the bowling ball and the feather would fall at the same rate, right? And so this is manifesting itself here in the sense that because the pendulum is bobbing back and forth due to the effect of gravity, the mass actually does not affect the motion. It would be the same motion regardless of if it was made of lead or of some thin plastic. All right. So there's a kind of general principle that I really want to address here, and that is that small displacements from an equilibrium being all the forces are balanced, almost always result in harmonic oscillations about the equilibrium. Now, there is an exception to this, which would be unstable systems. This is for stable systems. Okay. So if you have a stable system, like a building should be a stable system, a bridge should be a stable system, the pendulum is a stable system, and you displace that system very slightly from its equilibrium, it is going to oscillate about that equilibrium, and more specifically, it's going to oscillate about it as a harmonic oscillator. And so this is why we talk about harmonic oscillators, because they're kind of almost universally found in all systems that attain an equilibrium, because when you displace those systems, you'll find these harmonic oscillations at very definite frequencies. This does require a stable system, so let me just kind of explain the difference. So a stable system would be something like a ball at the bottom of a pit that's going to slide back and forth around the pit, right? So the equilibrium would just be the ball at the bottom of the pit, and if I displace it, then it just swings back and forth. Okay, that would exhibit the behavior of a harmonic oscillator. So this is stable. An unstable system would be one whose equilibrium is like a ball on top of a hill. And in this case, if I displace that ball from the top of the hill, it's just going to keep falling and roll off away from that equilibrium. So this is a stable equilibrium, and it is characterized by the fact that oscillations will tend to bring you back to the equilibrium point, and this is an unstable equilibrium where you being even slightly off brings you way away from your original configuration, not stable configuration. So the right hand side is kind of like, if something that's balanced on the knife's edge, and the left hand side is like something that's very secure and well balanced. Something that if you knocked it over, it would just come back down. Okay. So that is this video. So one comment on the math here. The mathematics in this video are pretty sophisticated, and it is being demonstrated to you for educational purposes, because this is the type of mathematics that's very common in physics and in some branches of engineering. The art of approximation is a very important skill to learn. So I am showing this to you to demonstrate kind of a classical system, which is the oscillating pendulum, to teach you some of its properties, like the fact that the period of the pendulum does not depend on its mass, and to introduce this idea of stable and unstable equilibriums, and the fact that displacements from an equilibrium, if they're small, will result in harmonic oscillations. I am not so much concerned about you guys learning how to do linear approximations, okay? So I did want you to see the idea of a linear approximation so you kind of know what it is, and when you see it in the wild, you'll not be too surprised by it, but I do not expect you to reproduce them on a test, okay? So you will not be expected to reproduce linear approximations on a test. So that's my one disclaimer, and that is the conclusion of this video.